Okay, so today's lecture we will go through the remaining part from the Berkeley course. So the only topic that's left is DevOps. As we've mentioned, DevOps is a practice that's recently got very popular. Where it used to be, Dev and Ops is two separate teams or two separate roles, traditional waterfall process. So, although we kind of already touched on some of the stuff related to DevOps, I think when we went through the Agile module last week, we've already mentioned ideas like continuous integration, where you have a automated system to, one click or even without one click, it tracks every single commit and then runs tests against that commit or that latest change. Similar, we've talked about Git and the Git workflow. That's also sort of related to DevOps, where I follow certain procedure when you commit those changes, push those changes, how you manage branches, and it kind of also relates to like how you do deployments, which we'll mention today. Okay, so instead of me introducing you to DevOps, I think it'll be a better idea just listen to the video. So without further ado, we will get to today's video.
One of the biggest changes in software lifecycle management brought about by software as a service and cloud computing is the combining of software development and software operation, or DevOps. Essentially, the same small team that develops a SaaS application is responsible for a significant aspect of its operations. This arrangement is great for Agile because it puts the developers that much closer to the customer. But it does mean that software developers now have to learn some skills that previously were the responsibility of a different team. How should the different components of software as a service, such as the web server, app server, and database, be deployed on specific computers? And how many computers will be needed to serve varying user demand? Whose responsibility is it to check for newly discovered vulnerabilities in those components, which may have nothing to do with your app's code? What kinds of monitoring must be put in place so that the DevOps team can rapidly detect if your app is down or behaving incorrectly? In the early days of cloud computing, developers had to handle all of these tasks themselves, and it could be pretty daunting. Early cloud offerings like Amazon's Elastic Compute Cloud basically offered you infrastructure as a service, or IaaS. You paid for the ability to rent the hardware, but pretty much everything else was up to you. But the rapid emergence of platform as a service, or PaaS, has made the SaaS landscape much more developer-friendly. A PaaS provider configures and operates a curated software stack containing all of the basic components needed to deploy specific types of SaaS applications. For example, HTTP servers, app servers, and databases. They employ professionals to optimize the performance of those components and apply security patches when vulnerabilities are found. Many PaaS providers even have the ability to automatically add and remove resources in response to varying demand for your app, and that's one of the very first benefits that was claimed for cloud computing. So, does this mean that now app developers can once again remain ignorant of the operations aspects of their software? Not by a long shot. In this module, you'll learn about the different meanings of performance and security as they apply to software as a service, and how to measure, characterize, and optimize the aspects of performance and security that are your responsibility as DevOps engineers versus which aspects you can entrust to a good PaaS provider. You'll learn why the performance and security issues that your PaaS provider can handle are probably being handled better than if you did it on your own, which is one reason we advise you to try to stay with platform as a service as long as it makes sense. But even if you eventually have to migrate away from PaaS, whether because of cost or because of the technical constraints that your PaaS provider cannot meet, a major insight is that the knowledge and techniques that you'll need to solve performance and security problems outside of PaaS are exactly the same ones you'd have to use to get the most bang for your buck while staying in PaaS.
All right, that's a quick overview of DevOps. Next we will see, I think next video will be about the definition of this role and then the responsibility and the goal of DevOps. So straight to the next video.
DevOps. By the way, anybody know what that animal is? Say it again? It is a sea cucumber. You see what I did there? I just thought that would be funny. Whatever. OK. I've heard that they're delicious, but frankly, I would be grossed out by eating it. So from development to deployment. So this is, when I started sort of seriously writing non-trivial amounts of code, which I guess was in grad school in like the mid-90s, this was not a thing that we worried about. It was relatively rare to deploy your code in the sense that we think of deploying today, where like anybody can put up a website, anybody can put up a SaaS application. That's not the way it was. So the bad news is it actually was not very easy. If you wanted to create a web app and host it somewhere, that was pretty complicated for both administrative and technical reasons. And that has now changed, obviously. The bad-ish news is that now you, the developers, also have to start to worry about some of the things that previously only operations people worried about. You have to worry about things related to security. You have to worry about things related to provisioning and basic performance as seen by your users. There's no longer this idea of, let's just throw it over the wall and the ops people will figure out how to make the right things happen. Just as when we started talking about the agile approach to testing and test-driven development, it is no longer the case that you as a developer can pawn off testing to someone else. You are responsible for doing a lot of your own testing, even though there's still a separate organization that, for example, maintains and builds testing tools and infrastructure. So the developer has sort of started acquiring more and more responsibilities, but at the same time, the slices of that you have to worry about have become nicely confined by things like platform as a service. So here's the things we're going to talk about in terms of what developers ought to know about operations. We'll do about the first half of them or so today, and then the remainder next time. Continuous deployment, the idea that you can and should be pushing new versions of your code out to the cloud all the time. Upgrades and feature flags. How do you roll out an important, big, heavyweight new feature without necessarily having downtime, which is not as simple as it might sound? What are the things that, as an application developer, you have to worry about in terms of keeping your customers' data safe? Versus what are the things that, as a developer, you actually don't have that much control over and is much more in the hands of the people running the infrastructure? Monitoring. If you're not monitoring it, it's probably broken. So as a developer, what level of monitoring is appropriate for you to keep track of about your app? And how do you know what you're whether what you're monitoring is good enough? So when we talk about we want apps to be available and responsive, what does that mean? How do you measure it? How do you fix the problem when you're not getting what you want? And what are some common measurements like AppDex that are used to capture kind of a very high-level, oversimplified view of how well your app is meeting customer needs, in terms of performance at least. And then finally, a lot of times when, especially for student projects, that there's this really big desire to, we don't want to use a relational database. We want to use a NoSQL database. Or, we're going to be the most scalable thing in the universe, so relational databases aren't good for us because they won't scale. First of all, they will scale. They scale really hella far. But the point is, even if you do end up running against the limits of things like the relational database, the kinds of things you'll have to do if you then have to roll your own are exactly the same kinds of things you have to do to avoid hitting those limits or to postpone hitting those limits in the first place. So we'll talk about different ways that you can be less abusive to your database. And for a surprisingly large number of apps, up to surprisingly high volume, that will be enough. So what's the big difference between development and deployment? When you're developing, you have a pretty good idea, you think, of what your app is supposed to do. So you write the code, you write the tests, And even though you're writing sad paths, most of the time you're expecting that the app is going to be used in a certain way, and your testing and your approach to writing defensive code sort of reflects that. In deployment, the question is, what does your app do when it is exercised in ways that it was never designed to be used? Not when a user leaves a certain field blank, but when they put garbage characters or non-8-bit Unicode characters in it. Not what happens when the user specifies invalid dates for a report, but they specify no dates at all. Or when the user tries to sort of create multiple copies of the same page to submit the form with different information different times. And unfortunately, it turns out that users are terrible, because if you didn't have them, it'd be really easy to keep your app running. So trying to predict the things that users might do can be daunting and discouraging. Also, some bugs only appear under certain conditions, in particular conditions of duress. So how do you reproduce, and how do you deal with bugs that are not easy to reproduce sort of with you just sitting at your workstation? Sometimes there are subtle differences between the production environment and the development environment, or even not so subtle differences. One difference that I think applies to a lot of the projects here is if you're deploying on Heroku, they use Postgres as their database, unless you go out of your way to change that. When you're developing and running your tests, you're probably using SQLite. Now, 99.9% of the time, as long as you're using Active Record, it generally shouldn't matter. But it turns out that there are cases when it does matter. For example, the way that strings are compared in certain database queries are case sensitive with SQL, but they're not case sensitive in the same way with SQLite. So how do you know if a bug is due to the difference between those environments, and how do you minimize them? If that weren't enough, the world is full of evil forces, people seeking to subvert your app and make it do not what you intended it to do. It's very common to think, I'm developing an app for some nonprofit. Probably only 20 or 30 people are really going to use it. They don't store any particularly valuable information. Why would anybody go after that little app? We don't really have to worry about evil hackers. The truth is you do, because most evil hackers don't care about the app. And for the most part, they don't care about the data. They want to use your app as a vector to do other things. They want to use it as a launching point for malware distribution, or for cross-site scripting, or other unsavory things we're going to talk about. So the reality is, just because your app doesn't seem valuable to the rest of the world, it actually is valuable as a vector. So you still have to worry about some of this stuff. And the world is also full of idiots. People who are not necessarily evil, but they're just incompetent, and they will do things that try to break your app, sometimes without realizing it. So this is sort of if you're an operations person, these are the kind of things that you think about, right? Bugs that only appear under stress. Well, when you're in your development environment, performance stresses are generally absent. It's just you testing your app one person at a time. If the bug only emerges when 10 different people try to hit the same database row at the same time, you might never experience that in a regular development environment, but it'll show up in operations. So these are the kind of things that historically, as a developer, you haven't had to worry that much about, and now you kind of do. So there's a number of different axes that you can break out for this. I'm going to give you one characterization, but it is not the only possible characterization. We can talk about availability. Some people call it uptime, which is just a simple scalar metric of what percentage of the time is the thing up and accessible. And as you can imagine, in platform as a service, there's multiple components to this, right? If it's down, it could be that your app is malfunctioning. It could be that something about Heroku or whoever your provider is malfunctioning. It could be something about the network between the user and the servers that's malfunctioning. So availability, even just captured as what percent of time, as we'll see, is a little more subtle than that. Responsiveness. Some people call it latency, but basically, if the user does something, how long until the application reacts and they get some sort of response. Scalability. This is a very, very loaded word, but in general, for interactive software as a service like we're mostly doing in this course, what people mean when they say scalable is, as you add more and more users, can you maintain your level of responsiveness without increasing the cost per user? So if you've got 10x as many users, but each user is still seeing about the same performance as when there were very few, then that's great, unless it's costing you more money per user to do it, right? If it costs more per user the more users you add, that's a terrible, terrible business model to be successful with. Privacy. Most people, when they say privacy, what they mean is some data should only be accessible to particular users, maybe because they own it or because they've been delegated authority to it. So privacy is, are you making sure that only people who should be allowed to view the data or modify it are able to do so? Authentication. When a user comes to your site, do you have a way to have them prove that they are who they claim? The most common way is something like a password. If they know the password, maybe that's who they claim to be. People who do security say that authentication can be something you are, something you have, or something you know. A password is something you know. Something you are is like facial recognition or the fingerprint things that are on recent model laptops. And something you have can be some sort of a physical token, like the hardware devices that will stick into a USB port and do a challenge response or something like that. And then data integrity. Once the data has been stored, is it at least tamper evident? Notice that it doesn't have to be tamper proof, but you have to be able to tell if somebody attempted to modify it in an unauthorized way. Very generally, we'll talk about the top 3 things as referring to performance stability as opposed to security, which are the bottom 3 things. So this is not the only categorization, but it is a reasonable breakdown in terms of the kinds of things that developers have to think about.
Okay, so that's a quick definition of DevOps. Actually, there's usually another term that describes the same thing, which is called site reliability engineering, or SRE for short. Google has published several books on that. You could just go to sre.google/books. I've read through their introduction in the first chapter. It's pretty solid, so it's also some good resources for you if you want to learn more about SRE or DevOps. So, so in this video, the professor divided DevOps into 2 major categories, which is performance and security. Or in these books, you'll see that it's broken down into reliability and security. So that's a similar idea, but I would say it's the Google's definition or the SRE definition is probably more popular. So anyway, the idea is similar. Okay, so let's get to the next video.
So our next topic is to talk about the shared nothing architecture that substantially all internet systems use today and what that means for scalability. And going back to our diagram, we started out at the top level asking about the connection between clients and servers. Now we're going to go one level deeper and look inside the server box to see what it's made up of. And as we'll see, there's 3 major building blocks that servers are generally composed of these days. There's the presentation tier or front end. That's a web server like Apache or Microsoft IIS. There's the application server. That's kind of where the action is. It's where your application code usually runs. We're going to be using one called Rack, which supports applications written in Ruby. And then there's a persistence layer or a storage layer or tier where data that's permanently associated with your application, like your customer data, would get stored, typically like a database. So in the old days, the web really began as a way for people to exchange static documents, graphics, and so forth. And early web servers had a pretty easy job. All they had to do was accept an incoming TCP request, figure out which file to serve, and get that file back into the browser. But very quickly it became the case that the more interesting sites were actually more like running a program and having the program generate the page you saw. And if you think about it, this is the case for things like e-commerce sites where you visit a page, you search for some products, and what happens is a program has to get run to find all the products matching your search criteria and build a page on the fly just for you. So originally, people authored sites like this by saying, well, HTML is what the browser consumes, but what we'll do is we'll find a way to stick a little bit of code here and there into the HTML, and that code is what's going to create the content on the fly. And it very quickly became clear that the code was the interesting part. So the code became the tail that wagged the dog. It sort of moved out of the web server into its own home in the application tier. So now we're going to look at these different pieces and how they work and what are the implications for architecture of software as a service. So if the site is really about running a program rather than about serving a static file, well, when you're going to run a program, even if it's from the command line, you have to worry about things like how do you figure out which program to run? So which URI coming into the site
How do you map a URI into the right program or subprogram? How do you pass arguments to that program? How do you get the program to run on the server? What happens if there's an error? Who cleans up after the program and provides the error messages? So all of these tasks have to be handled in SaaS apps as well, except that instead of running programs from the command line or directly through a GUI, we're running them as the response to a request from a web browser. So because all of this kind of functionality has to be taken care of no matter what language you use and no matter what framework you use, frameworks have evolved to sort of support all of these common activities so that you don't have to. So really today, it's more like you fill in the code that's specific to your application, and all these other details like mapping URIs to which piece of code and how do you pass arguments from maybe stuff that the user typed in, how do you pass those to your code, all of those things are now taken care of by the framework. It saves a lot of work. Now, even within the logical architecture, where we said that there's these 3 different tiers, that's just a logical diagram. Another question is, how do those things map onto physical hardware? Now, in the case of the homeworks you're doing in this course, or when you're doing your own development of your own SaaS applications, typically you'll have a single machine that's hosting all of the pieces. So, this gray box here you can think of as your laptop, and on that same machine you're running your own web browser to test things. You're running some kind of a presentation tier, and we're using WebBrick, which is a really, really simple development web server that ships with Rails by default. It can only handle 1 user at a time, so not great for big sites, but it's fine when you're developing your own code. In purple, we have the application tier, which has an app server, rack, that provides some of the machinery around allowing your Ruby code to run as part of a Rails SaaS app. We have the Rails library itself, which your code can use. And then finally, we have the storage tier where permanent data lives. Well, in development mode, the only permanent data is data right on your computer that you're using really for testing. So we're going to be using SQLite, which has a very good name. It's like a SQL relational database, which we'll talk about more in the next few segments. But it's so lightweight that only a single user at a time can use it. So this is kind of the baby version of the setup that's fine for one person developing and testing. When you move out into a production environment, typically you'll see something like this, where you really have multiple copies of the entire stack. You'll see that we've replaced WebBrick with Thin, which is a production quality, very fast, very lean front-end presentation tier. We have many copies, so to speak, of the application stack that includes the presentation layer and our application code. And the reason we're able to do this, remember that we said previously HTTP is a stateless protocol. Every request is truly independent. Well, if it's really true that the only thing that ties together different requests from the same user is data that would be put into this persistence tier, then we should be able to create multiple copies of the app to serve many more users. We should be able to direct incoming traffic to any one of those copies because they're all independent requests and rely only on the stored data to tie together requests from different users. And this is, in fact, exactly what's done. Now, the reason it's a little bit more difficult, why I haven't drawn multiple copies of the database, and I'm using MySQL as a stand-in here, the database is a little more tricky because as soon as you have multiple copies of the database, that means there might be multiple copies of some data items. And now there's the problem of whether those copies can always be kept in sync if there's multiple databases. That is an open problem, and if you've heard about the NoSQL movement or of NoSQL databases, it is one of the problems they try to solve. And we're going to try to shed some light on what's difficult about solving that problem momentarily. In this course, we're going to be using Heroku for our deployment. They have a very similar environment, but they've custom engineered what they call dynos, which are sort of lightweight app servers that they can run. And each app also has databases devoted to it. It's got database caching built in so that commonly done database queries can be easily repeated. And they have their own technology for a bank of presentation tiers, HTTP servers, so that they can scale those out separately from the application servers. But the basic idea that we're coming back to is the same. The stateless parts of the stack, like the presentation tier and the app tier, can essentially be scaled out by making many copies of them. And with cloud computing, it's so cheap to have multiple machines that this is a very popular strategy. But sooner or later, the database is likely to become your bottleneck, and scaling that out is much more tricky, which we'll come back to in a moment. So what do people do when it's time to scale out the database? If you've heard the terms sharding and replication, one thing you might say is, well, if I have some data elements that are really not shared across different users, for example, my personal preferences, my user profile on a site like MyYahoo, well, one possibility is I could actually have multiple databases, and users whose usernames start with different letters might be stored in different databases. Now, that works really well as long as you never need to combine information from two of those databases, and then things can get pretty hairy. But this is called sharding, and the idea is that if you have some data that really never has to interact with other data from different users or from different entities in your application, you could just store that data on different databases. Replication is another solution. This says, well, why don't we have many copies of the database and only one copy accepts updates, because the idea is that updates happen less frequently than queries. And periodically, the updates will get propagated to the other copies. This is often called master-slave replication, and it's one way to do this. So what kind of data is it the case that reads occur much more frequently than writes? Well, think about Facebook and the idea of posting on a timeline or liking something. There's many more people who are going to consume the results of that than people who are updating it at any given time. So having some amount of inconsistency actually has been an issue for Facebook that they've done a lot of engineering to work around. It is the case that if you do an update to your timeline, there's a bounded amount of time during which not all of your friends will see it right away. They'll see it at slightly different times. Now, to their great credit, Facebook has done an enormous amount of engineering to minimize that window so that in practice, most people never even notice it. But the message here is there's no free lunch. If you try to scale your way out of the database problem by replicating, you're going to have the issue at some point where different copies of the data might not all be up to date. If you try to get out of it by sharding, you avoid that problem, but now you have the problem of data that's in different databases. It's really hard to combine and join together. So neither one of these is a solution to the database scaling problem, and it arises directly from the fact that in this three-tier architecture, scaling where the data is just hard to do. So to summarize the high points of the software as a service architecture, the browsers are the clients. They ask questions. They make requests to the servers. HTTP is the protocol that they use, and they use URIs and HTTP methods like get and post to name what they want to do. HTTP is a request-reply protocol, so everything begins with a client asking a question. Servers can't really push information to you proactively. They have to wait for the client to ask. Even in cases where it looks like the server is pushing information, it's really usually just the client asking over and over again. And in modern SaaS applications, when you make a request to a server, it's not going to serve you a static file. It's going to generate some content on the fly for you. HTML is the medium by which that content is encoded. CSS, or cascading style sheets, is how we control its visual appearance. And because HTTP was designed as a stateless protocol, cookies allow the servers to track different clients and to keep track of the same client coming back on multiple requests. So there's an important architectural trade-off that was made here, right? The architectural trade-off is stateless means you can actually scale out those middle tiers by replicating the app server or replicating the presentation tier in a way that you can't really do with a database. So in retrospect, you could argue that even though statelessness seems to introduce the complication of requiring cookies, on the whole, it was a good architectural choice because it allows parts of the application to be scaled much more easily. Frameworks like Rails and like Django and like others try to collect some of the common machinery necessary to support SaaS apps, like the machinery we've been talking about, and make it conveniently available to use so that not every new programmer has to reinvent the wheel. And finally, the mapping between these logical tiers and the shared nothing architecture, frameworks are responsible for giving you that too. They have to identify where different functionality goes, how the framework supports each piece, and that's what we'll explore in the next couple of segments.
All right, a quick comment on that. Though the three-tier architecture is largely true, I would say for the persistent layer, other than the database, there's usually also a storage component to it, especially for application that allows user to upload images, files. There's usually a storage involved, and then similar to database, like in order to have an application to be scalable, I need to have some sort of solution so that all the application servers can share the storage. Usually typical solutions are like cloud storage, like S3, but also other solutions I've seen are like network file system or NFS to share the storage through over network for the entire web application fleet. And then there's also solutions out there. But yeah, just a quick comment. Usually other than the database, which is persistent, there's also file stores that also should be persistent. Okay, we'll get to the next one.
So we started last time talking about the idea of performance stability and different aspects of performance that you might care about. And we're going to continue that discussion now. We talked about scalability as this sort of overused term, but that we agree for software as a service, when we say that it scales, we mean that you can take on more and more users. The performance or the response time seen by each user remains stable, and the average cost per user doesn't go up, right? Obviously, that would be kind of a bad thing. The response time is actually one of the key metrics in software as a service because that is the user's experience of performance. You may be really happy that your site is processing millions of queries a day or whatever, but if the speed that each user perceives that they are being served isn't good, that's kind of the performance that they care about, right? From the time I click to the time I get back something useful and can continue my session, how long is that? So typically you're measuring the number of users per server per dollar spent or something like that. And the goal is keep that response time more or less under control as that number goes up and as you add hardware. People also talk about the throughput or bandwidth. The truth is that bandwidth really is only important in as much as it helps you serve the number of users you want with good performance. So if your performance per user is not that great, very often the reason for that has very little to do with bandwidth to your service, or maybe has even very little to do with the number of servers. So we'll see some examples of that. So one of the ways that this is measured is called a service level objective. And basically, this is a sort of a statistical representation of how a service ought to behave. If we think about the time to satisfy a single user request, we can call that the latency, the response time, whatever you want. The SLO asks the question, what percentage of users are seeing acceptable performance? And you sort of get to define what acceptable means, although there are some pretty well-established thresholds. Typically, the way this is done is you set a percentile, you set a target response time, so that's kind of your performance target, and you set a time window. So for example, you might say 99% of user requests take less than 1 second to return a response to the user over any given 5-minute window. Right? So the time window is actually pretty important because in some sense, the smaller you make that time window, the less you can get away with. Right? If you say 99% of requests over a month, you could have a couple of minute periods where the requests are going to hell and you'll still make your 99% threshold. And the people who came in during that low period are still going to be really annoyed. So the SLO is always measured over some window. Some number of minutes is typical. 2 nines, which is 99%, is sort of a lower bound. Some people go for 3 nines. A service level agreement, if you've heard that term used instead, technically that's actually the legal term. So the service level objective is the quantitative measurement of what you want to have happen. The service level of agreement is the lawyer's understanding of what happens when you fail to meet your service level objective. So in general, we'll talk about SLO rather than SLA. So SLOs have been sort of the coin of the realm for measuring the performance of a typical cloud service as seen by its end users. But measuring percentiles over seconds, there was a desire several years ago to essentially come out with a simplified metric that, as a single scaler, could give you, how are you doing on your SLO? Because if your SLO is this, and it turns out that instead of 99%, you're getting 98%, technically you're violating your SLO, but still you would like a metric that captures the fact that at least you're close to what you said. So a simplified metric that is quite widely used, and I'll show you today a monitoring tool that measures it for you, is called the AppDex score, which is sort of short for application index. And the way you calculate it is really simple. You pick whatever your threshold latency is for user satisfaction. So this is the number that you're aiming for. And you say that a request that takes less than that amount of time to get a response is satisfactory. Those users are happy. If the request takes longer than that, but less than 4 times as long, you say that the user tolerates the behavior, although they're not necessarily thrilled. And if the requests take even longer than that, then those requests, you basically get no credit. Right? So the way to think about this is you get full credit for requests that come in under the threshold. You get 1/4 credit for requests that come in you get half credit for requests that come in between the threshold and 4 times the threshold. And then that fraction of the total request is your aptX score. So it's pretty easy to see that if all of your requests come in under the threshold, this simplifies out to 1. Something in this, kind of 0.85 or above is generally good. Most sites that have some credibility, will shoot for sort of the high 90%. You have to be careful about systematic outliers. So the sort of canonical thing that can, skew results like this is you have some critical operation that users really care about, but it doesn't occur very often. So you might have an operation that takes 10 times as long to do. Clearly, that's far outside your target window. But according to the aptX score, if you do the math, as long as it doesn't happen more than once every 15 requests or so, you'll still be greater than 0.9. So as with all of these metrics, there is no single metric that gives you the, this is the absolute threshold, ground truth, above is good, below is bad. aptX is one indicator, but you have to take it in context with other things. So along with aptX being, in a reasonable range, you also have to make sure that there aren't sort of outliers like this occurring where a small fraction of your users are consistently annoyed at you. So you can try to visualize this. And I'll come back to response times pretty soon. But this is a graph taken from the technical blog on New Relic, which is a nice monitoring service that comes as an add-on to Heroku. And they've highlighted, in this case, they've set the aptX threshold at 1,000 milliseconds, or 1 second. And basically what you see here is these are, the yellow requests are the ones that are coming in strictly below the threshold. Those are good, full credit. The requests in red are between 1 and 4x the threshold, so you get kind of half credit for these. And all this stuff out here, which you can see, this goes all the way out to 8,000 or 8 seconds. It would probably go even farther. So one thing to take away from this is actually realistically what request curves look like, right? Most people, when you think of the distribution of request times, you like to think that it's sort of this nice normal distribution shaped thing. But in practice, what you see is that the tail is extremely long. And that's the thing that aptX is trying to capture. It's trying to give you partial credit for the fact that this is rarely shaped like a nice symmetrical bell curve, but not so much credit that these people out here aren't being considered. So we'll have other definitions of this. We'll have a little bit more to say when we talk about responsiveness. Now, by the way, in this example, I said that the aptX threshold was chosen as being 1 second. And in a moment, we'll talk about how would you go about choosing a reasonable value for that threshold. But be aware that from this picture, I actually sort of did the math here, and this represents an aptX score of about just under 0.5. That isn't very good. But if I could justify saying that actually 1.5 seconds is OK, by raising my threshold by just half a second, my aptX score magically goes up to 0.7. So, and of course, the farther into the red you decide to move this threshold, you can make your score get as good as you want. So there's a legitimate question of what reasonable behavior means for your users. And we'll come back in a moment to, people have actually done experiments on this. Like, at what point do users get annoyed? At what point do they get fed up and they just leave your site and they give up entirely? So before we come back to that, what can you do if your site is slow? And in general, if your site is pretty small, the simplest thing to do is just over-provision by a little. Pay for a little more capacity than you need. And certainly in the presentation and logic tier, so the web server and the app server tier, you could just create multiple copies of them. So we'll talk about situations where that does and doesn't help. Before cloud computing, this was very painful to do because you had to rack your own servers. Today, it is basically automatic. In fact, there are add-ons and companies that will do this on top of platform as a service for you. So if all you really have to do is kind of keep your site within the platform as a service that you're using, and it's just a matter of scaling the amount of logic up and down, then you're golden. That is a great place to be because, as we said last time, the cost of individual additional server columns is pretty cheap. Certainly, it's cheaper than programmer time to try to make the code go faster. If you have a large site, or if you have a site that sort of doesn't fit this simple platform as a service model, it's a little harder to do that because if you've got 10,000 servers, you don't want to over-provision by 10% and have 1,000 idle computers. So what this comes down to is the insight that we mentioned last time, which was the same kinds of problems that push you out of the simple, PaaS-friendly, kind of everything is managed for you tier. Those are the same problems that will come back to bite you if you're trying to do all this yourself. So whether it's trying to use a NoSQL-like database, whether it's trying to do your own server provisioning and server scaling, essentially, all the things that we're going to talk about today, time to glass, avoiding abusive database queries, all of those same problems come up no matter where. So learning to solve those problems while you're still in a sort of nice PaaS tier will actually take a lot of grief off of your hands.
Okay, some more comments on that. I think that AppDex is a very helpful measurement in terms of measuring the performance of a web application. Before that was introduced, it was actually difficult to tell if an application is slow or not. Like one straightforward way would be just a binary, like is the server down or up? And then let's just say if the site is up, then there's nothing to worry about. A little bit better would be is the site slow, like just by opening the page and say, oh, if it exceeds like takes longer than a second to 10 seconds to load up, then we'll say it's slow. But then that measurement is not really specific enough because usually in a web application there are multiple pages. So by just testing a few pages, you actually never know how the other pages would perform. Also, depending on the context, the status of the user, is the user logged in or not, the behavior may change, and so the response time may also change. Others would be like if there is cache involved, like sometimes you'll hit a page that has already all the caches in place, so it can be really fast. But let's say the cache expires every 10 seconds or so, then every once in a while you will hit the same page, but then without the cache, the page may be really, really slow. So like without AppDex, it's really difficult to measure, like on average, how a site performs. So AppDex is really a help for a measurement. But usually it's difficult to compute that yourself. That's why in the video, the service which is called Neuretic is mentioned there. I've used Neuretic quite a lot. So, and I actually don't think there's other services out there that offer the same measurements. So usually what you will do is just plug in the service and then you will see the measurements out of the box. And then with that index or that measurement, you can better measure and understand the behavior, the performance of the application. Yeah, so that's that. The other thing I want to mention is that, in my opinion, always prefer to use PaaS or platform as a service whenever possible, instead of using IaaS or infrastructure as a service. Even the cloud providers like Google, Amazon, within their IaaS or infra offerings, they also offer a platform as a service on top of that. Like what I use a lot for AWS is Elastic Beanstalk, and then they have other similar offering that's an alternative to Elastic Beanstalk. What those PaaS ultimately do is they offer a CLI tool that you can just one command or one click and deploy the application. And that really takes away a lot of responsibility and effort needed to set up servers and scale out servers when the load increases, stuff like that. And back then, like we had a project involved a team of a couple of people, and then we basically developed a sort of a PAS, or not really PAS, but the DevOps pipeline, all these continuous integration, configuration, continuous deployment, which we'll talk about soon in the coming videos, and auto scaling, that kind of thing. It took the team, I think it took like half a year to just get that built out and then running a stable state. But if I now reflect on that project, it's really not that productive, although it's a good learning experience to understand what's going on underlying the whole PAS thing or DevOps thing. But really, when we talk about productivity, it's almost always much more convenient and easy to just run and operate applications on top of PaaS rather than using infra as a service. It's just a huge amount of work to set up stuff like that. But there are times when an application gets too big or too complicated or needs some special customized setting, some middleware in the server, you never know. But sometimes it will be needed, but otherwise always go for a PaaS or something like that. All right, so next let's get to the next video.
How do you do upgrades? And this is an issue that arises when you have upgraded code that is either rolled out to many servers or where there's an incompatibility between the code being updated and the database schema. So I'll give an example of each of these. If you're using multiple servers, so if you have a large installation, you've got multiple Heroku columns, let's say, then at some point, you're going to have a situation where there's an instant in time where some servers have the new code and some still haven't been updated. So either you shut down your app during that time and you only turn it on again after all the servers are updated, or you have somehow taken steps to make sure that even if the two versions of the code are both running, the app doesn't break. And that can be a little bit tricky. Or a similar scenario, even if you only have one server, you're about to roll out a new version of the code, but the new version of the code also includes a change to the database schema. So and in particular, it's a case where it's not backwards compatible. So if you were to roll out the schema first, it would break the app because the current code can't deal with the new schema. If you were to roll out the app code first, it would break because it needs the new schema in place. So again, you have this awful choice of, well, you could either shut down the entire app from the user's point of view, do all of the upgrades, and then bring it back up, or is there some more graceful way to handle this if you can't afford to have your app be down? And by the way, a schema migration that actually includes modifying data could take minutes. So it might be a significant amount of downtime from the point of view of the user. And if you're a site that has users in different time zones and stuff, you can't assume that, oh, I'll just do it at 3 in the morning when nobody's up. Somebody is always up. So what are the two approaches here? The naive approach, and by the way, if you can do the naive approach, you should do it. If you know that your users are never online between 2 and 4 in the morning, that is a great time to do this. You take the service offline, you do whatever has to be done, including migrations that won't work with the old code schema. You deploy the new code, you deploy the new migration, you make sure all the servers are up to date, and then the app comes back up. So the users don't have access to the app during this intermediate state when it hasn't been fully updated yet. The only downside to doing this is that there is downtime. And depending on the app, the downtime could be a matter of less than a minute, in which case maybe it's not a problem. Or it could be minutes or worse, in which case it's a problem. What does this look like for a sort of a typical Rails app? Here's a hypothetical example where the change that I'm making is previously I had just a name field, and now instead I want to have first name and last name in 2 separate fields in the database. That means that every place in the app that manipulates names is going to have to know about this change. and the old version of the app won't work with the new schema and vice versa. So if I have the luxury of bringing down my service, I can just shut down the service, and then I can apply this migration, which says for every single moviegoer, and there may be millions of them, in the database, update create the two new columns, first name and last name, and then for every single moviegoer, populate the columns from whatever the existing name field is. So the logic is pretty simple, but if there's a lot of users, that could take a really long time. And you may or may not have the luxury of bringing down the application during that time. Oh, and of course, by the way, once that's all done, I can remove the old name column because that isn't needed anymore, because the new code is only going to look at first name and last name. If you can afford to do it this way, you should do it this way. This is simple. You can back up your database immediately beforehand so that if something goes super awry, you can restore your database. You can do all of this under the covers while the app is not available to the users, and you can do it at 3 in the morning when only CS169 students are awake. In fact, you could even be fancy, and you could wrap that entire migration in a transaction so that if anything goes wrong in the middle of the transaction, the whole thing is blown away as if nothing had ever happened. Of course, that takes hella memory and hella more time, but if the app is already going to be down for a while anyway, again, this is the simplest brute force thing that can work, and I am a big fan of using simple brute force if that will suffice. But what if brute force does not suffice? If you don't have the option of taking your app down and you need to do this in a sort of transitional way, then you can use this really cool thing called a feature flag. And here's the general approach. I'll sort of walk through the code, but you kind of break it into steps where in the first set of steps, you do non-destructive migrations. What does that mean? Maybe you're adding new columns to the database, maybe you're adding tables, but you are not destroying or changing any existing data or any existing schema to make sure that you don't cause any problems with the existing version of the code. Then you deploy your new code protected by a feature flag, which I'm about to show you what that is. But TLDR is that a feature flag is a condition in the code that basically says, if we're in a situation where we're dealing with records that are in the new schema, do this over here. But if the situation is records in the old schema, do that over there. And by the way, once you've done that over there, migrate those records to look like the new schema. It's very cool. I'll show you in a minute. Once the code is deployed, turn on the feature flag. That will start activating the code path that allows the records to be lazily migrated. Once all of the records have been migrated, you can deploy new code that lacks the feature flag. And finally, you can delete the old schema parts that you don't need anymore. So again, let me show you a concrete example which should make it more clear. And this is the same scenario, by the way. The scenario is that we want to change it from being first name, or from just a single name field to first name and last name. But this time we're going to do it without any downtime in the application. Okay? So here's what we're going to do. The first part is the top half dozen lines. We're creating a migration that adds the new columns for first and last name. It does not change or modify in any way the existing data that has a name column with the entire name in it. So it's just adding stuff. It's not destructive. And you can run that migration. That's quick to run. You don't need any downtime for that. Then we're going to deploy a new version of the code that does the following thing. You'll notice we've also added a column called moviegoers, which is Boolean, migrated in the moviegoers table, which is Boolean valued. And basically what we're going to do is for every row in the moviegoers table, we're going to keep track of whether that row has or has not been migrated to the new schema where first and last name are separate. So here in our new version of the app, we're going to create two different basically scopes to condition our active record queries. We're going to say we're using the old schema if the migrated column is set to false. We're using the new schema if it's set to true. And we're going to have basically a method that says when the find matching names method, which is like one of the places that the code has to change in order to accommodate the schema, there's basically going to be two versions of that method now. So in the old code, basically if we have a feature flag that once we flip it on, we'll basically say how do you find somebody by name if you don't know which schema they're in? Well, it's moviegoers that are using the new schema. Then the condition is the last name or the first name match the string. Moviegoers that are using the old schema, it's basically just a single match on a single field. So if the feature flag is turned on, meaning it is now, you may now assume that you're dealing with either version of the schema, the logic of this old method has now been changed so that on a row-by-row basis, it'll do the right thing. Basically, what used to be one query has been turned into two queries. Otherwise, if the feature flag is not turned on, then this is the logic that would have been in the old method, right? So basically, the old find matching names method was just this one line. We've wrapped that line in an else. So what's the net effect of doing something like this? The find matching names method is basically going to allow the code to work correctly under either schema. And in particular, some records in the table will have been migrated, and their migrated flag will be set to true. In that case, they'll be included as part of this first clause. Some records in the table will still be using the old schema, in which case the migrate flag is set to false. They will be caught by this clause of the query, and the two queries are just union together. Okay, so see what I did there? I basically created a version of the logic that is prepared to deal with records from either schema and combine them in the right way. The other cool trick that we have to do is anytime one of these records is modified, so if a moviegoer goes in and modifies their profile or anything happens that could change the record, that is a great opportunity to take a legacy record and move it to the new schema. So here's a function that does just that. Basically, as long as the unmigrated legacy user has a name that looks like it can be split into a first name part and a last name part, it will set those records in the database row for that customer. It will set the migrated flag to true. And where am I calling this? I'm using the before save active record hook. I could have put it somewhere else, but it's an interesting use of an example of the lifecycle hooks. So basically, this says anytime any moviegoer is about to be saved, before finalizing the save, do these things. So this has the effect of one at a time, whenever that user happens to be saved, it will update them. It'll set their migrated flag to true. So over time, more and more of the records will be in this migrated true new schema. Fewer and fewer of them will be in the old schema. Maybe there are some users who never log in, and at some point I just say, OK, I'm going to mass migrate all those users using some sort of a background job. So the only thing left to do is somehow this new name schema feature flag has to be flipped on. Just deploying this code doesn't do anything. But once I deploy the code is running. I'm confident everything works right, because this is the only method that's being called, right? I haven't turned the feature flag on. Now I do whatever is necessary to turn on the feature flag, and all of a sudden now the code can go down either path. So the trickle of migrations from one to the other begins. And then once I've either migrated all the users over or decided that, for the users that I haven't had a chance to migrate over, they're inactive. So I'm just going to start migrating them over anyway, and I'll run a background job to trickle that. At some point, it'll be the case that none of the users have the old schema anymore. At that point, I can do two things. First of all, I can deploy a new version of the code where this legacy stuff is entirely gone and the references to the feature flag are absent. Second, I can then run a migration that deletes the old name column, because now I know it's not really being used anymore. It is no longer referenced anywhere in the code, so it's safe to delete. So we'll finish up this example, and I'll show you another cool, tricky example on Tuesday. But this is basically a good template. You do the non-destructive parts. You put in code that is conditioned on a feature flag that can deal with either the old or the new version. Once that code is sort of running and humming along, you turn on the feature flag and you let the code start doing its thing. And once the migration of the data is done, you can deploy code that leaves out the feature flag, run a new migration that gets rid of the old stuff you no longer need. And at no time did you have to take your app offline to do that. You can keep your app running the whole time.
OK, so another quick comment on that. I don't really think the professor made a good example here. Like in practice, I almost never have to go with either approach. Let me get the video back. Like that's the example for the naive approach. Practically, usually what I do with that, something like that, is just don't remove the column, which is the last line of code in this example. And by not removing the column, usually it doesn't break anything. And then with that, you could either deploy the new code or run the migration. Either way, it will work out of the box. And then once the entire migration is done, and then the code is in production, you could then run a separate migration to remove the deprecated column. So that's actually almost always the case for almost all the applications I've developed and maintained so far. So yeah, I mean, the naive approach is not really that, usually it doesn't really need a downtime as long as you don't do anything destructive during the migration. And then you could always delete the column and do something like that afterward. But I do see like the other approach there, like sometimes when an application gets really, really complicated and requires some really fancy logic to handle a new and old version, then this approach will be needed. But otherwise, usually, like a non-destructive, naive approach should be surface. And then even for that same idea applies for applications that has a client piece or a front-end piece plus a back-end or API endpoint. So whenever you need to launch a new feature, usually the case is you either have to update the back-end API first or have to release the new front-end application first. In those cases, it's also a similar idea. Usually you just keep the API, all the fields in the API same with some extra fields that's needed to support the new feature, and then release the new client-side piece, and then go back to the backend API piece to remove the deprecated fields. But also, it's kind of similar to this naive approach, even for a client backend, client server kind of application is still similar. That just do something non-destructive first for backend, and then release the new front-end code, and then remove the unnecessary part. And that's almost always what I do. And I don't really see the necessity of going with the pure naive approach, because it really just saved one step by adding a new column and then removing the old column in one migration. But in reality, usually it can be just separating two migrations, and you can just, and since the stuff we talked about, right, all the deployment should be one click or one command, so there's not really too much effort needed to separate one migration into two. But again, that's my opinion. So yeah, just for a reference. Okay. Next we'll talk about monitoring, and I think that's actually the most important piece in terms of DevOps. So we'll get to that now.
So, responsiveness and monitoring. How do you pick an aptX threshold, and how important is it to get it right? And and what are there tools that can help you monitor so that you get alerted when things go bad? So, is response time important? Yes, response time is important. Now, granted, you're not Amazon, you're not Google, you're not any of those people, but what the effect, if those companies do measurements on what happens if you essentially introduce an artificial delay into the user's experience, those companies have enough users that they can actually measure, in a statistically significant sense, the effect of that one change on their service in terms of their user behavior. So this was done not quite 10 years ago, I think. Amazon did a study where they injected up to 100 milliseconds artificially of latency into the response, and they saw a 1% drop in sales. 1% doesn't sound like a lot, but 1% of Amazon is a lot. Yahoo did the same thing back when Yahoo was relevant. Yeah, I know. They injected up to a 400 millisecond delay in search results, and they got 5 to 9% drop in traffic. Google did it. They injected up to a half a second delay, 20% fewer searches. So that's extremely noticeable, right? Speed is not an optional thing. There's also two sort of classic studies that are striking because even though they were done more than 30 years apart, these were studies of people using interactive applications. And the idea was the user does something to the application and how much time elapses before the application sort of visibly responds so that they know they did something. And what both of these studies found is that if something happens within 100 milliseconds, it's basically the same as instant, right? So in some sense, there's almost no point in getting below that threshold because from the point of view of human perception, that's kind of the shortest interval people experience. And if it's greater than 7 seconds, that's when people's attention starts to wander. Like that's when you're in danger of losing them. Or if you have a competitor site, that's where you're in danger of having them click over to your competitor site. That's called the abandonment time. Now, of course, the reality is if the user is doing something important, like some online banking thing, they're not just going to abandon, right? They're going to wait. But the point is they're going to be annoyed because that's the threshold at which, if it was a non-critical task, they would have abandoned it already. And these two studies done 30 years apart confirm the same thing. So that suggests that there's something about our brain wiring. And by the way, there is an intermediate threshold in there of about a couple of seconds. There's a threshold beyond which the user loses the sense of causality. So what I did is what caused the app to react that way. That's a little bit less relevant for SaaS applications because the application doesn't sort of do things on its own, right? It tends to do things when the user stimulates it in some way. So these thresholds are actually pretty stable and well established. And they have led Google, and in particular Jeff Dean, a Google fellow, to coin the phrase, speed is a feature. And Google has an enormous collection of tips ranging from the very basic to the extremely esoteric for people who want to make their web apps respond faster or even make their static pages load faster. They have done a great deal of research about this. Having said that, before you dive into this developer's website, there's a number of sort of low-hanging fruit things you can do to make sure that you're getting the basics right in your app. So we're going to start with that. So if speed is a feature and if responsiveness is so important, where does the time go? So if you're looking at an application that is running as a cloud app, first of all, when the user's browser, by the way, the column down on the right, this is sort of one column of the SaaS servers. This is a second column. The column on the left is the timeline as seen by the user. So the request has to travel across the network, right? Time goes down the page, but usually getting across the network is not the critical step. That's not in the critical path. When it gets to the server, it's got to be processed by some piece of hardware. It's got to be routed to an appropriate web server, which is connected to an app server for your app. So in our case, that all happens within Heroku somewhere. Then from our app, probably it's going to try to do something interesting with the database. So that's a component. Then it's got to render the views or whatever the response is. Maybe it's just a JSON object if this is an API. And finally, it has to go back out through the OSN network stack and start sending packets back to the user's web browser. And we can distinguish, so the response time is when everything is done, but we can distinguish this intermediate point that used to be called time to glass. I know a lot of you are young, but this is when actually monitors were made of glass instead of LCD. So people called it, the time to glass is basically when does something first appear that kind of looks like the page the user is expecting to load. So from the time the first byte is delivered, well, it can't render the page with just the first byte. But web browsers have become pretty good at, as soon as the HTML is loaded, even if the other assets are not yet loaded, like images and JavaScript and so on, there's enough that it can sort of start rendering the outline of the page, and the user's like, something's happening. So that used to be called time to glass. Maybe now it's called time to LCD plastic or something. But there's usually a longer gap between time to glass and the time that the entire page has been loaded. So at this point, all of the rendering is done. Any JavaScript has been loaded. Any external assets like images and things have been loaded. And the page is basically ready for anything to happen. Right? Browsers spend a tremendous amount of effort to do as much work as they can during this interstitial here. So as soon as things arrive in the browser, they get loaded. And when we talk about JavaScript next week, one of the challenges it presents is that your JavaScript code may begin to run before your page has been fully loaded. And you need to sort of be aware of that fact when you're writing code that sort of assumes the page is going to look a certain way. So, like I said earlier, this is what most people sort of think response time looks like. It's a nice bell curve. So, people who are 2 standard deviations out are getting response times that are, or 95, the 95th percentile is around 2 standard deviations out. So those are the users that are still, getting served somewhere within 2 standard deviations of your target time, which is here. In reality, that is not what response time looks like at all, because I showed the real example from the previous slide. Here it is again. And just sort of superimposing, if you actually look at the mean, the average, if this were a bell curve distribution, the mean of all these things is here, right? The median response time is there. And as you can see, the mean and the median look nothing like the bell curve. And in fact, if you ask the question, what is the behavior that 95% of users are getting, right? What guarantee can I make to say 95% of users will do no worse than this? It's way out at this point. And you can see that this is actually even farther out than what AppDex recognizes, right? This is way out on the tail of AppDex. So clearly, this 95th percentile is way more than 2 standard deviations of a bell curve out. But this is really more what real life looks like. So if you're the designer of the site, really what you're worried about is this stuff out here, right? What is the experience that most of your users are having? And if the best you can say for 95% of users is it's no worse than about 6 3/4 seconds, that's really far away from your AppDex target time. So those are the kind of things you look for when you're monitoring your site to understand where the time is going. So what tools can you use to help you do that? That brings us to a discussion about monitoring. And the rule of people who do operations is if you're not monitoring something, it's probably broken, which is kind of a harsh way of saying, if you're not monitoring it, how do you know it isn't broken? What are the things that you can monitor? At development time, there's actually quite a bit of monitoring you can do so that even though the performance of your development machine is probably nowhere near your production machine, the kinds of things that can go wrong, in other words, the conditions that could cause bad performance in production, can often be detected in development, and you can sort of fix them before you go to deployment. So for example, later in today's lecture, we're going to talk about how to detect if you're doing needlessly abusive database queries. Those queries will still run faster in production than they will in development, but they're abusive. And that fact can be detected in development before you deploy. And then, of course, in production, there's at least 2 kinds of instrumentation, and they're both really important. Internal is instrumentation that in some sense is embedded in the app. So it can get its hooks into the Rails framework. It can get its hooks into the app server. If you want to answer questions like, in a typical request going through my app, how much time is spent in my controller method? How much time is spent looking up stuff in the database? How much time is spent rendering a view? So you basically want to break down the pieces of a request. You need to have hooks in the framework that will let you do that. On the other hand, the other kind of instrumentation is the kind that probably your users care more about, which is from the outside, what does your site look like? Does it work? What is the response time? And in fact, from the outside could really mean anywhere in the world. So to do a good job with the second one, you actually want to be sort of sending probes to your site periodically from all different places to simulate the idea that your users could be anywhere. So internal monitoring is obviously important to help you develop the app and sort of tune the app's methods to not cause needless bottlenecks. But external monitoring is sort of the gold standard because it's kind of like, to the same way that cucumber scenarios are in some sense more realistic because they represent what a real user would do. In a similar way, you could say that external monitoring is more representative because it tells you what the user experience is like from the outside. And it's not just that if your site is down, you can detect if your site is slow for reasons that can't easily be measured by the internal monitoring. So as an example, suppose it's the case that I have my internal monitoring set up from the moment my controller gets the request to the moment that my view is rendered and it's been sent out into the world, right? My internal monitoring is going to capture all that and hopefully tell me some interesting intermediate points in between where things are happening. But if the problem is that I don't have enough servers allocated, so users are actually lining up in a queue waiting to get into the app server before the controller even sees that request. Right? That is something that, depending on the kind of internal monitoring you use, may not be visible to you because it isn't inside your app. Right? That's queuing that's occurring at the moment before your app gets control of the request at all. It's happening in the web server tier. So having a handle on what the big picture looks like as seen by the users is what you get from external monitoring. New Relic, which is one of several monitoring solutions, but it happens to be a nice add-on that, with one click, it sort of just works in your Heroku app. And by the way, you should just have New Relic turned on for your Heroku app all the time. The free tier gives you a lot of useful information. I'll show you some screenshots from a real app in a moment here. But typically the way it works is that there's some piece of the monitoring system. In this case, there's a New Relic gem that you would have to include in your production section of your gem file. That's the piece that actually hooks into various parts of the Rack app server, the Rails app, and actually instruments when interesting things happen to a request. And then there's also a piece that usually runs outside. So in this case, it runs, for example, at New Relic itself. That will do some external probing where periodically, like once every couple of minutes, it will send a predetermined type of HTTP request, which you can define what it is. It'll send it to your app, and it'll make sure that it gets back a response within a reasonable time frame that you specify, and that you can do some simple checks on the content. So the simplest thing you can think of is get it to load the home page of the app. Something that doesn't require login, it's stateless. You know exactly what you expect the answer to look like, so you can check for the presence of particular strings on the page, just like you would do in a really simple Cucumber scenario. And you just have it, once a minute or so, ping your app and make sure that it's still running. And if more than 2 or 3 in a row get missed, then you can have it alert you and do something. And then tied into all of the instrumentation that's being collected is some application that you, as the app owner, can interact with, and you can see all of that monitoring. This is New Relic plugged into one of my Heroku apps. By the way, look at my awesome AppDex score. I'm doing so great, 0.96, but I have my AppDex threshold set really high. It's set at like 7 seconds, so I am totally cheating. I can change it at some point, but the truth is the app is relatively low traffic, so I'm not that surprised. But here's sort of the last few hours of just requests coming into the app, and you can see that it's color-coded by where the time is being spent for each of those requests. So this sort of very light green is request queuing. That is, Heroku has accepted the request from somebody's browser, but the app server is too busy, and there's sort of a queue, and the request has to wait in line before the app gets to handle it. Right? So that's an example of one of those components of waiting time that is definitely experienced by the user, but in some sense is not the fault of your app stack because your app hasn't even gotten to touch it yet. Middleware is basically things like Rack, time spent in the Ruby interpreter, which you can see the light blue actually accounts for the majority of time on most of these requests. Accounts for the majority of time on most of these requests. Time spent in the database, Postgres. For the most part, it's pretty small. There's a few requests where it's a little bit larger. Web external, like here. That is my app making a call externally to some other services API and how long that takes. Right? If my app is blocked waiting for the response to come back, again, that becomes part of the response time experienced by the user. So I'll show you more of that in a moment. And then the outline of all of those, right, the sort of convex hull, is the response time. I'm just on the free tier, but even if I scroll down here, I get a bunch of useful info. For example, it's telling me that the place order method in the store controller is the transaction or the kind of interaction a user might do with my app that overall has the longest average service time. So you can see that even the other slow actions in my app, all complete in under a second. But for whatever reason, this one is twice as long. It typically, and I believe those are averages over the time window of the previous graph, which is like 12 hours. So why does this one take twice as long? And I can imagine, especially if my AppDex threshold was lower, I might say, OK, well, I want to go in and figure out how can I make my AppDex better? Well, one thing I could do is I could find which operations are the slowest ones right now. I could also find how often those occur. And if the slow operations are ones that occur frequently, I should focus my effort on what can I do to make those go faster. So if I click through that, which just in case I had internet problems, I did on another screen here. So here's a bunch of different methods in my app that are sorted by the slowest average response time. And there's place order right at the top. But if I look over here, and now it's breaking down, when these requests happen, where is the time going? Look at this brown. This brown, if you can't read it from back there, says it's the Stripe API for doing credit card payments. Notice, by the way, that the New Relic hooks are smart enough to actually figure out that that's what I'm calling. So it's actually looking at the outgoing service request and figuring out what site they're going to. And what you can see from these little spiky things is that almost all of the response time of these requests is dominated by time spent out there, right? So it'd be great if I could make my place order action run faster, but the majority of the time it takes to run is the time that Stripe takes to return a response to me. So unless there's some way I can figure out how to do that call faster, like, I don't know, maybe there's like a higher level of Stripe service that I'm not paying for or something. But in general, what this tells me is I'm not going to have a lot of luck improving my responsiveness by working on that method, because most of where it's spending its time is not something that I control. And this is sort of, the first insight of trying to do any kind of performance tuning is before you change anything, try to figure out where the problem is. And having this kind of monitoring makes it way easier to figure out where the problem is. I could also sort these by most time consuming, which isn't the same thing, right? So, and this is useful to know too, because although place order still shows up here, but if I sort these by where is the most cumulative time being spent, store controller index actually accounts for nearly 40% of the time spent in my app total by everybody. So that would suggest that maybe a better investment of my time, if I want to improve performance, is maybe I should go after that method, because that's the method that most users are spending the most time in. Therefore, that would be a good one to speed up. Also, if I can speed up the methods that are most frequently called, I can serve more users with the same number of dynos. Right? So if you think of a dyno as basically a serving engine that can serve one user at a time, and there's a queue building up behind it, if you don't have enough dynos, the people who are in that queue, they're going to start seeing those queuing delays that I showed on the first page. Right? You're going to have more people waiting in this request queuing phase, which happily right now, you can almost, there's like little teeny bits in here, but it's almost insignificant. But a benefit of finding the most frequently used actions and making them faster is I can get them out of my pipeline quickly. So the implication is with the same number of dynos, I can serve more users. Right? So it depends on what is, if all you're trying to improve is make response time low and it doesn't matter what it costs for now, find the ones that are taking the longest and see if the place they're spending your time is something under your control. In particular, for the ones where it's the database taking a long time, I'm going to show some techniques that you can use to try to speed those up. But sometimes what you find is that it's not your fault. So this and everything on here, this is just the free tier of New Relic. I don't work for New Relic. I'm not an investor or anything. I just think it's kind of a cool service. And given that the free tier already tells you way more information than before Platform as a Service, getting this level of detail would have been really painful. So I just leave it turned on all the time. And yes, you can set it so that if your AppDex ever drops below a certain threshold, or if the average response time over some short window goes above a certain threshold, you can basically have it notify you. You can have it send you an email or text you or something. And that's super useful as well, because believe me, you want to get that email from New Relic as opposed to getting it from your customer. And sometimes just rebooting the app is enough to sort of make the problem temporarily go away. So this is why I'm a fan of New Relic. What can you do when it's an external call to an API and it's not your fault? So there's a couple of things, right? A lot of APIs will have two different versions of a call, synchronous and asynchronous. And in the synchronous version, you make the call and you sit there and wait for it to come back. In the asynchronous call, you get a response immediately, but the response says check back later for what really happened. So you can use the first version of the second version, the async version, as a way to show something to the user. And maybe what you're showing to the user is just like a spinner saying, transaction and process. And then you check back later and you get the real answer. But if it's a synchronous API, like in my case, 2 seconds is about what it takes to call Stripe and get a response back. There's nothing I can really do about that. Well, that's not true. What can I do about it? I can't do anything about that two seconds that Stripe takes, but I can make sure that everything else around that, the parts that are my fault, are squeezed down to the minimum. So if I know that I can't do anything about the delay of Stripe, at least I can make sure that I'm not making it worse by adding delays inside my app that I might have been able to avoid, right? And this is, by the way, this is actually Google's philosophy. Their philosophy is that any app that you put on top of Google is going to add latency. So their goal is to drive Google's latency like close to 0, because then it's not their fault, right? Which is an admirable thing to do. That makes them a better person than me. OK, I had some static screenshots here, but honestly, the best way to get familiar with New Relic is go to your Heroku app deployment and just add New Relic as an add-on. It's free, and it just works. The only thing you have to have is the New Relic gem in your gem file. And I think you have to get an API key so that they can report results back to New Relic. But you'll get some amazing insights on what your app is doing. Even if you're just sort of playing with your app interactively in your staging server, you will get interesting new insights on where the time is going in your app. Highly recommended.
All right, a couple of comments. First, I want to say the last statement from the professor in this video is kind of wrong, because even like for Strep, there's no asynchronized API for him to consume. Usually what a developer can do is use some sort of background processing, task queue, job queue, stuff like that to handle it. So even though the API may not be asynchronized by itself, the application itself could actually send that synchronized API call to an asynchronized procedure with some sort of background process. And that way, he could actually, return the request early by showing something like a loading, a spinning thing, and then check it again later once the actual request finished. So yeah, that's that. And then I want to emphasize again on monitoring, especially for DevOps, that if there's nothing set up, or if there's only one thing to be done, it's really setting up the monitoring first. Because not only, so in this video, the professor shows how to use monitoring to improve performance. But a lot of times, when we talk about DevOps, we also think about reliability, doing all sorts of troubleshooting, firefighting, when certain site goes down or gets really slow. Like without monitoring, there's just no way to tell what went wrong. I still remember my first job where the server, I was tasked to manage the server and then make sure the site is always up and running. And the first incident I encountered, for some reason, the site went down, and I realized the logging, that even the Apache access log was disabled, completely turned off. And then later, I was told that it was turned off because the storage is running low. So in order to save storage, they sort of just turn it off, completely off. Although there's probably a better way to just let it rotate pretty quick, but still have some log there so that we can investigate issues. Yeah, stuff like that. No log, no monitoring. It's just completely blind troubleshooting that issue. So there's no way to tell, was the traffic increased, or was the hardware have some failure, or was that some other misconfiguration in the middlewares, or was the program or the application code got changed. Back then, my first job, and the first instance, there's just no way to answer any of these questions. So that's why, and then without that, you cannot really do anything. Like in the video what just said, like if it's not monitored, it's probably broken. And if it's not monitored, there's no way to tell if something is broken, and there's no way to tell if something is fixed. And also, there's no way to tell what exactly to be improved. Like the example shown in this video, one request, one controller action might be really slow, but it can be just largely because of a external API call that's really slow that you might not be able to do anything about it. So yeah, in DevOps, usually, so in addition to performance tuning, when we talk about troubleshooting, usually the first question is, have the traffic changed, right? Because if the traffic doubled, it actually makes sense that server goes slow because you just need to provision more computing power to it. Was the hardware or the infrastructure failed? Like sometimes hard drive fails, sometimes CPU, memory, and those hardware can fail. Without monitoring, you cannot tell. And if that's the case, was the network bottlenecked? Was the external service went down? I actually incurred quite a few instances back then. There was a depending third-party external service, and then the application, almost every page or every request of that application needs to make a call to that external service. And then that service goes down every once in a while. Before setting up monitoring, there was no way to tell what caused that. But as soon as we have visibility to that, then we clearly know it's actually external service that could cause problem. And lastly, was there any change to the application code? Because sometimes, a new feature gets delivered, and then the implementation of that feature introduces some performance issue, or there might be a bug that causes infinite loop. You never know what developer might end up doing with code changes. So with monitoring, you could also answer, like in New Relic, there's a feature to integrate with like a Git service that every time you push a code, push a change, or integrate with some CI service, anytime you run it, you deploy a change, it sends a ping to New Relic, and then you can see exactly at what moment a deployment was made. So yeah, that's about monitoring. And also with monitoring, you kind of have a baseline of how an application has been performing, and then sometimes when you're investigating to an incident, you sort of can compare with the baseline. If the application has always been slow for that specific request, then maybe it's just a user making more of that kind of request rather than the application itself had some issue. Yeah, so that's about monitoring. And if there's only one takeaway from today's lecture, that is always, if possible, always set up some sort of monitoring before things go wrong. All right, let's get to the next one.
The one aspect of performance tuning we didn't talk about with databases was caching. And no, this is not on the exam. We already clarified that. But this is an important enough concept that even though we don't have a homework assignment about it, for the same reasons as I wanted to explain how indices work and why it's important to index foreign keys and stuff like that, this is kind of in that same category of ways to be nice to your database and get a lot more bang for your buck out of the database. And again, even if you, despite doing this, you outgrow the platform as a service solution, you're still going to have to worry about this if you get big enough that you've got to roll your own. So basically the observation behind caching is the fastest database is the one that you never have to query at all because you already have the information you need somewhere else. So there's a number of ways that you can do caching, but one of them is the most obvious, is that if the data underlying some particular query hasn't changed, then you shouldn't have to repeat that query. It would be nice if you just store that data somewhere and be able to retrieve it without having to do a repeated query. Also, sometimes doing the database query isn't even the most expensive part of the app. If you remember our New Relic graphs that we get, it sort of shows you how much time was spent in Rails, how much time was spent in the database, and then there's how much time was spent rendering. Rendering is actually pretty complicated, right? Because it's sort of assembling a page out of all these different pieces. So sometimes if the data hasn't changed, and therefore the views that are rendered based on that data don't have to be re-rendered. So if you could just keep a copy of the pre-rendered views around and serve them automatically, that would save even more time. So as with any system where you're going to introduce caching, you have to make a few decisions. Like, first of all, what do you cache? And in our case, there's at least in SaaS applications built around Rails, which is representative of how other frameworks do it, there's at least two choices. You can cache essentially an entire page at a time, or you can cache parts of a page so that if you assemble a page from pieces, the pre-cached pieces save you some time. And then you have to decide, how do you know when the cached versions of things aren't valid anymore? In our case, basically the pattern is the truth lives in the database. So when the database changes, any views or parts of views that are based on those tables in the database may change and have to be invalidated. So we'll have an opportunity to see another design pattern in action for this. As with a lot of these things, my goal is to give you the architectural idea of how this works in Rails, which is very similar to how it works in other frameworks. So I'm actually not going to show a lot of source code today. If you're interested in reading the details and seeing more examples, there is a Ruby on Rails guide for how caching works. There you have more source code examples and stuff like that. But my goal for the course is just to give you the content. And if there were a final, this would be on it, but there isn't. So I just hope you'll pay attention anyway. So where can you cache things? If we start all the way at the browser and end all the way at the database, there's actually a number of places, right? So the name of the game in caching is, if the request is going in that direction, how early can you turn it back? Because you can serve it without going any further. So most of you probably are aware that your browser has its own built-in cache of pages. Part of the HTTP protocol is to negotiate when a page served from a server is no longer considered to be valid or might not be valid. But if you try to reload that page within that time limit, the browser will often be able to get it from the browser cache, and then you're done. You didn't even go out to the internet. If that doesn't work, the next stop is the web server. So that HTTP front end, remember that the web server is the last piece of infrastructure that sees the entire HTML page as it's going back to the client. So if the web server could be assured that the most recent version of a particular page from your app is still valid because the data underlying it hasn't changed, then the web server can actually return the entire page from a page cache, which is actually a huge win because that request never even makes it to your app. Like your controller doesn't even see it. So for pages that don't change very frequently, page caching actually can be a major win because the Rails stack doesn't even know that those requests happen. What if that fails? Because there's no page that matches in the full page cache. The next thing you might try is the action cache in the controller. When would you use that? Well, basically, and I'll show an example of this, but there are cases where even if the page content hasn't changed, there is something about the app logic that has to run to determine if it's okay to serve the page. Canonical example of this would be something like an action that you have to be logged in to do on the app. It may very well be that the content, the page you would see corresponding to that action hasn't changed since the last time you visited, but there has to be a check for you being logged in, otherwise you're not allowed to go to that page at all. So these are cases where effectively you are still able to serve a copy of the entire page, but there is some application-specific logic that has to be run first to sort of make sure to give it the green light. And in Rails, that's done with what's called the controller action cache. If that doesn't work, because maybe the page is out of date, there is still the possibility that if you've been using partials to create your pages, I think some of the more complex apps probably have them, but a partial is like a chunk of a view. And you can pull in the partials, for example, like if you're rendering a collection of model instances, it's very common to have a partial that represents one instance and then just render the partial multiple times. It turns out that with a small change to your view code, the moment that you render a partial, you can also tell Rails, please cache this. And the idea is that once again, if the data underlying that fragment or that partial doesn't change, then in the future, when that page is rendered, rendering the partial just means pulling it out of the fragment cache, as opposed to recomputing what the actual tags and content should be. And Rails manages most of this for you, and in particular, they try to name things in such a way that when the underlying data changes, the fragments, it's easy to identify when the fragments have to be invalidated. So I will show an example of that. And then lastly, if none of those works, you have one last hope, which is that at the level of the actual model, the model queries the database, and if that particular query has been done recently, and the database certainly knows whether the data for the query has changed or not, the database also has a query cache. So in this case, you've paid the price of having your application do the work, but you might still be able to save on having to send one more query to the database. And in the scheme of things, that's actually still good, right? Because everything to the left here is stuff that runs on stateless server columns. You can replicate more of those. That's just spending more money. But anything that saves work on the database and gives you more bang for the buck out of your database is worth doing, right? So these are sort of 5 different places where caching could happen. Database caches and browser caches are pretty standard. The levels of caching in between vary somewhat depending on the framework. So for example, because Rails has this built-in concept.
Okay, I'm just going to pause this video right there. Since we're running short on time, if you're interested to learn more about caching, you can visit that link back then. Also, the completed version of this video, you can find it in the edX Berkeley course. But the idea is there, so there can be multiple layers of caching. And although we haven't touched on invalidation yet, but you feel free to watch the full video later to learn more. But in general, I would say don't over-optimize it unless super necessary, because usually by introducing caching, it kind of complicates the logic. And then by introducing multiple layers of caching, it makes the logic even more complicated, and then make the invalidation even more tricky to do, because often what you will see in some CMS, like one of the CMS I had experiences is Drupal, and Drupal has all these layers of caching in place. And what you would sometimes run into is you purged a cache from one layer, but there's that same cache in another layer. So even though you purge some cache, the stuff is still cached somewhere else. Yeah, and then my advice in general is just, unless it's necessary, just don't introduce cache. And then when it's necessary, just do the necessary part, and then just don't over-optimize it. And then whenever possible, just implement the cache in this diagram, just as much to the left as possible. Meaning if it's possible to cache in browser, just cache it in browser. If it's possible to cache it in web server or the page level, do that. It basically saves the most resource. Usually that's the case. Okay, so I'll just skip this video since the next video has some important thing I do want to go over. So let's go to the next video.
Be nice to your database. Your database loves you. It wants to help. But there are things that you can do to make it not have to do needless work. As we've said, the sort of biggest, the thing that you dread hearing about trying to move off of your current platform as a service is you've outgrown the database. Once you've done that, then you have to take some serious action. Then it's not as simple as just adding more dynos or more capacity. So there are ways that you can relieve the pressure on the database to sort of put off that moment as long as possible, and maybe forever. Like I said last time, all of Pivotal Tracker basically runs on one honkin' enormous database, but it is really just a regular database from the programming point of view, right? It's nothing special in terms of the stack. So you have to get at least that big before you'd have to worry about it. So what can you do? Use caching to reduce the number of times you hit the database. We'll talk about that on Thursday. But today we'll talk about 2 other things. There's a canonical problem that if you've taken a database course, you may have heard of it. It's called the N+1 query problem. and there are some simple ways to detect and avoid it. And use database indices judiciously. This is some of the lowest hanging fruit in the universe. So let's take a look at the n+1 queries problem first and what that means. And basically, it means that you're inadvertently doing n+1 queries when you have an association of has many and one thing owns n other things. So like a movie owning n reviews. What you meant to do was just get all the reviews associated with a movie. What you end up doing is n separate queries to get each one. So I will show a code example. OK, so what's happening in this code? So the intent here is I'm going to what did I do here? OK, I remember. So this is back to the moviegoer example where there's a relationship between movies and moviegoers. And in particular, given a moviegoer, you can find out all the movies that they have reviewed. So we're going to say that they're a fan. So we're going to find a bunch of fans, all of the fans in some certain zip code. And we'll come back in a moment to why actually even that line could be improved. But for now, don't worry about it. So we have a bunch of fans. Each fan's a moviegoer. Because there's a has-many relationship, in my view, I can say for each fan, look at all the movies for that fan, and then print out something interesting about them. And this is sort of the textbook example of the n+1 query problem, because the problem is that as I go into this loop in my view, fans is already an enumerable collection of the moviegoers. No problem there. But now, every time I say fan.movies, then for each one of those moviegoers, I'm now doing another entirely separate database query, right? So if you think about it, at the moment that I was getting all the fans, I already know how I'm going to use that information. In particular, I know that I'm going to dereference each fan and ask which movies have been reviewed by that person. So it would be nicer if essentially at the same moment that I'm retrieving all the fans, during that same database query, I would like to also retrieve the associated movies that go with them. If I could do that, then by the time I get into this loop, essentially this stuff will all be in memory rather than triggering additional database queries. Right? So the reason it's called the n+1 query problem is up there, line 4, that's the one query I'm doing to get the fans. But now for each of those fans, for the n fans, I'm doing another query to get the movies associated with them, even though I knew from the beginning that that's what I was going to do. I knew I was going to use that information. So the fix for this, most frameworks have some way to fix this. If you were writing a raw database app where you were doing your own SQL queries, you would basically do a multi-table join in line 4 to bring in all of the related information at once. In Rails, you can do that by telling active record when it does, here's the revised version of the query. Now, at the end of the query, I'm going to say includes movies. What does this mean? This is a hint to active record that even though the query is on the moviegoer table, one of the things that I'm going to do with the result is eventually I'm going to dereference the movies associated with each one. So if in database parlance, this will actually cause the join with the movies table to happen, and all in one query, you'll get back the entire big blob of stuff. And the moment you start traversing it, you will have everything already in memory, and it will not generate any additional queries. So what's the moral of the story here? This is a story whose moral we have seen before. The idea that in line 4, we get some fans, and in lines 8 and 9, we're trying to dereference the movies for each fan. That is a leaky abstraction, right? The code on top will work, but it represents an extremely naive and poor use of the database. The code on the bottom is a much better use of the database, but we've sort of broken the cleanness of the abstraction that you can just sort of say has many and then magically have those items appear, right? It's not magic, it has a cost. And here, we're explicitly acknowledging that we know that the underlying implementation of this object graph is a database, and we know that we have to give the database a hint about how we're going to use that data. So this is an example of another place where an abstraction leaks. If you do not understand something about how the abstraction is actually implemented and provided for you, you're liable to inadvertently abuse it, right? So, and by the way, do you have to sort of manually go through your app and find every place where this occurs? Well, that's a good exercise that's left for the reader, but you do not actually have to do that. There's a gem called Bullet that will actually do this for you. And if I had a little bit more nerve, I would try to show this live. But basically, you just fire up your app and use it, like in development mode as you normally would. And at the bottom of every screen of your app, the Bullet gem will insert a little box saying, here's a place where you could have eagerly loaded this other table, and it would have avoided the n+1 query problem. It will also tell you the opposite, which is, here's a place where you had an includes. In other words, you told the database to eagerly get all that data, but then you never ended up using it. So you kind of made the database do the extra work, but then you didn't take advantage of it. So it's super, super cool. And like most of the gems, all you have to do is put it in your gem file and activate it. OK, so that's the code for my example. But the better version is the one on GitHub. So don't worry about the fact that it got cut off on the slides. So sorry. OK. So by the way, just to make clear, there's more than one way to do this. The naive way is you can first do a database query for an object, and then you can explicitly do a second query for the owned objects, the has many association. I find that it's much nicer to just use includes, because you're actually, the text itself is actually telling you what it's doing, right? This is the main query, but I'm going to include additional joins that I know I'm going to use later. Was there a question in the back, or was it just, yeah? Yeah, so the question is, can you have basically more than one includes, so that if you have a traversing multiple associations kind of a thing? Yeah, so and you can actually do a lot more than that. If you look at the active record associations documentation, includes is just one example of a thing you can put here. You can also, for example, do a query that's conditioned on a join, and the where clause makes references to the other table. So for example, suppose I wanted to say, not just for every movie I want to eager load the reviews, but furthermore, I only want them in the case where the average review score is greater than some number. In my single query, I can also say joins reviews, and then I can have a where clause that refers to something about the reviews table associated with each movie. And it will construct the correct single query to do all that filtering for you. So basically, in almost any situation where you have two tables that are related in some way, and you want to do a query that is going to either pull in and use information from the multiple tables or wants to be conditioned on any aspect of the multiple tables, there is some active record query loading construct that will help you do it. You should never, ever end up having to write like any SQL queries to do this. Some of them are a little hard to get your head around, but they all work. OK, so that's one of two classic types of abuses that you can avoid is n+1 queries. Deploy the bullet gem, run your app. The first time you run it, you're probably going to get hits all over the place. A related thing that you can do, and maybe even easier, is indices. So when you tell the database something like, find me all movies where the rating is a particular value, the naive way that would be implemented is it has to actually scan the entire table of movies and look for matches. It would be a lot better if there was basically an index, or essentially a reverse hash, that would allow it to find any, in sort of O of one time, identify all the rows where the rating matches a particular value. So it's basically, internally with databases, it's implemented in a way that's similar to a hash table. So the basic rule is whenever you have a where clause and you're going to condition the query on some particular column, heaven help you if you don't have an index on that column, because the alternative for the database is it now has to do a complete scan of that table and look for matches, which means that the longer that table gets, the longer that query is going to take. Once again, a leaky abstraction, right? Ideally, we would just like to say, whenever we say where rating equals PG, we'll just get them back. But if you don't have an index on the rating and the movies table gets larger and larger, all of a sudden, with no changes to your code, that query will start running more and more slowly, and you won't know why. It's an even bigger win if the attribute is unique valued. So for example, if you've already set a validation on one of your, let's say on your user model, where only one user is allowed to have a particular email address. So you're guaranteeing that you'll never create multiple users with the same email, or whatever else you want. If the attribute's unique value, you can actually tell the database that. You can give a hint to the index builder saying, I promise that if I say rating equals PG, there is at most one movie that will match. Then you can build a really hyper-efficient reverse index to do that. So if indices are so great, why not just index every column? Like, why doesn't the database sort of do this automatically, and then you wouldn't have to think about it? Well, for one thing, it takes up more space. Because now, in addition to storing the movie information itself, you're also storing another data structure whose size is proportional to the size of the movie table itself, right? Which basically serves as the reverse index into it. But the real reason is that every time you modify the table, you also have to update the index. And that's where the real cost comes from. So if I've got a model that has 10 columns and there's an index on every one of those columns, when I add or modify any row of that table, there's 10 indices that have to be updated to go along with the updating of that one database row. So indices don't cost much, but they're not absolutely free. So you should be a little judicious in how you use them. And by the way you use them is you put them in a migration like anything else. There's a migration method called add index, and you basically tell it which column or columns you want the index on. So what do you index? What are some good things to put in an index column? Well, the foreign key columns, and this is probably the most important one that is most easily missed. For example, in our running example where you have reviews, and the reviews table has a column called movie ID, well, presumably the reason that's there is you want to be able to say something like, find me all of the reviews that correspond to this movie. But if you don't have an index on that column, then again, you're talking about a table scan. So basically, anything that is a foreign key, if you plan to ever traverse the association, and you probably do, otherwise, why would there be a foreign key? Basically, always index a foreign key column. Because if you don't, then trying to traverse the association guarantees you'll do a table scan. Any column that appears in a where clause. If you don't index the columns that are explicitly in the where clause, again, you're forcing a table scan. And this is one of the examples of sort of insidious bugs that in your development environment, they won't really appear, right? Your development environment usually includes a small amount of fake data. So database queries that get slow because the tables get big are just never going to show up as a problem. Happily, the bullet gem, I believe, will find index problems for you. And there's another one whose name I forget, but it's coming up in another slide, that does the same thing. It basically looks for queries that would have run faster if you had had an index. Columns that you sort on. If you're ever doing an order by, or if you're trying to get sorted results out of the database, having an index on the sortable column will speed things up. And at least as of last year, there was a gem called LOL-DBA for Database Administrator. I don't know if this gem is still around, because gems turn over fast. But if this is not the one, search GitHub or Google, because there's a lot of gems that solve this problem. Basically just making sure that anytime a database query happens, it can detect whether an index would have been useful. And most of the gems that do this will do this by actually querying the database. The database itself usually logs queries that were stupid because they should have been supported by an index.
So for the first bullet, if you're in the reviews table and you want to find all the reviews that have a certain movie ID, like wouldn't you practically speaking rather go into the movies table and use the movie ID to do movie.reviews?
It depends on which direction you're going in. So if you have a review and you're now, well, let's see. If you're, let me think of the sense of the example. Yeah, no, I think the explanation was right. If you have a movie and the question is, show me all of the reviews corresponding to this movie, the only way to do that is to find the table or the rows in the reviews table that have a particular value of movie ID.
Why not just go into the movies table and using the movie ID, do movie ID dot, like the dot reviews for that?
That's exactly what I am doing. So if I have a movie and I say movie.reviews, the query that corresponds to that is in the reviews table, all reviews whose movie ID field has the value for that movie's.
Oh, I see.
See what I'm saying?
Oh, right.
Right? So basically, so again, if you don't have an index on the movie ID field, there's no option other than to sort of scan everything in the table.
Yeah,
so
I
that,
forgot how the keys like actually work on this.
yeah, so by the way, that's the kind of thing that, I don't know, makes this a good exam question. Just saying. Anyway, okay. So where are we at? So if you do this, how much does it help? We actually did some benchmarks very much along the lines of rotten potatoes. And this is taken from a table in the book, but we sort of looked at a table where there's 2,000 reviews, 20,000 reviews, and 200,000 reviews. And what happens if you're trying to do queries based on movie IDs? How much better do things get if you have indices versus not, right? So for example, with just 2,000 reviews, there's already 166% performance improvement if you have an index on that movie ID field versus not. And you're sort of randomly, I pick 100 random movies, and for each one I ask what are the reviews associated with it. And then as you can see, as the table size gets larger, the absolute amount of time to do the query gets larger. So here we're at a point with 200,000 movies. It takes over 5 seconds just to do the table scan. I think this was with MySQL on some reasonable box, right? So you're 5 seconds for a database query. There's no way you're going to make your aptX threshold. Unless, like me, you cheat and set it at 7. But there's a historical reason for that, which is a good one. But the performance increase is substantial. And the penalty from having the indices, so if we create 1,000 random reviews, it takes that long to do it. If we create 1,000 random reviews in a version of the reviews table where every single column has an index, it's only 17% slower. And this is sort of like perversely bad because we don't need every column in that table to be indexed, only the ones that are foreign keys or that participate in where clauses. But the message here is the relative performance penalty of an index is not that large, and you can always delete an index later. So err on the side of having things indexed if you're not sure, because the penalty of not having them is awful, and you don't have to tolerate it.
Okay, that's about it for the entire Berkeley course. We skipped a few videos, and early in this course we skipped the entire module for JavaScript, but we technically pretty much went through everything offered by this course. And then you can always go back to the edX platform to find the videos that we skipped. And then for DevOps, there are a few remaining videos, but I'm also just going to skip it. And then the last video, we basically talked about some tuning for database query. And then I think these two, the one is indices and the other is M+1 query. Is probably the most important thing when you hit performance issues from database. Although like DBA itself is a huge thing that you could learn more, but yeah, this course is pretty much an introduction of everything, so we won't be able to get to the details. And then for this entire SRE or DevOps, you could, like I mentioned earlier, you could always learn more from these books. And then a few years ago, I also offered a course for DevOps. You should be able to find it in my YouTube channel. Unfortunately, that course was delivered in Chinese, so for people who don't speak Chinese, I mean, hopefully later, some point, I will deliver the course again in English. But otherwise, these books here from Google, they're free, by the way, so feel free to just go to that page and then grab a copy of these books, and you could definitely learn a lot from these books about SRE and DevOps. And then pretty much every single video we've watched today, there's a lot more details and depth goes into it. Okay, so that will conclude the main content for this course. And next week, there will be just bonus content, and then we'll just take it easy and I have a review lecture to just go through everything we've learned. But yeah, otherwise we will conclude everything today. All right, so I guess I'll see you next week. And remember, if you have not yet started your final project or final essay, it's really the time for you to get started. Okay, and then if you have any question, like if you want to have some idea about what you write about for a final essay, feel free to reach out to me and I can give you some examples and some ideas for you to consider. All right, then I guess I'll see you next week. Bye.